Okay, in this case, we're going to look at which forces might be involved and whether we think the mechanical energy will be conserved. So a bungee jumper rapidly decelerates as he reaches the end of a spring-like bungee cord. Ignore the effect of air resistance. Since the bungee cord is spring-like, we will be looking at a spring force. Therefore, the total mechanical energy be conserved. As the person slows down, that slowing down, that reduction of kinetic energy is going to be stored in the bungee cord. B, a girl releases a softball from rest at a height of 2 meters above the ground. The ball free falls to the ground. Forces doing the work, that's the force of gravity. Now, at this point, we need to also, they didn't say to neglect air resistance. If we assume there's going to be some air resistance, then we would assume the TME would not be conserved. The gravitational potential energy will be converted into kinetic energy, but some of it will also be converted into heat and other forms, and thus the ball will not be as fast at the bottom as it could have been had it fallen in a vacuum. C, a weightlifter briskly raises a 200-pound barbell above his head. Forces doing the work. This is an applied force. Okay. Is TME conserved? The answer here is no. The object is gaining gravitational potential energy with no offset of kinetic energy. So the force applied is being used to increase the gravitational potential energy, and thus positive work is being done, and thus the TME is not conserved. And finally, in letter D, a swimmer pushes off the blocks to accelerate forward. Again, that's the kind of applied force, the key here being accelerated. They were at rest. They're now going to be getting faster. That is an increase in kinetic energy for no appreciable change in the gravitational potential energy at this moment. Yes, they will start to fall, but right now we're just talking at the beginning of the race. They're just pushing off and speeding up. Okay, in the last set of questions, we're looking at whether the total mechanical energy should be conserved. And again, we're looking, when we ever talk about mechanical energy, we're talking about an object, so the object itself is highlighted. Okay, so a force applied to a root beer mug to accelerate it across a level countertop. Okay, the countertop is level, and the potential energy is staying, therefore the potential energy is staying the same, but it's getting faster. Therefore, the total mechanical energy must be increasing. We have an increase in kinetic for no loss of potential. Force applied to a cart to raise it up an incline at constant speed. Now, it's not gaining kinetic energy, but it is gaining potential energy. So in this case, the force is causing it to go higher and therefore gain potential energy for no loss of kinetic energy. Therefore, the total is increasing. 7, a marble starts from rest and rolls down an inclined plane. Ignore friction. It rolls from rest and rolls down the incline. This time, gravity's doing the work. We're ignoring friction. It's going to speed up, which means it gains kinetic energy, but it's at the same time rolling down the incline, so it's losing potential. So it's actually converting the potential into kinetic. A physics student runs up a flight of stairs at constant speed. We're again right back to number 6. We're not having any offset in the kinetic energy for the gain of potential energy. So that's going to be B. Baseball makes its flight through the air. We're neglecting the air resistance. The only force acting on a projectile, which this ball would be, is gravity. Since gravity is the only force doing the work, the total mechanical energy will be conserved. Yes, it will slow down on the way up, but it's also gaining height, so it's converting its kinetic into potential. On the way down, it will speed up, but it's losing height, so it's going to convert its potential into kinetic. 10, a coffee filter is released from rest and falls with terminal velocity. Since it's falling and not increasing its speed, we're actually losing our some total mechanical energy in this case. The air is being moved out of the way, so the force being applied by the air resistance is causing the total to become less. 11, a car skids to a stop while traveling down a steep hill. This is TME decreases in 2 ways. It's slowing down, thus losing kinetic, and it's going down a hill, thus losing potential. 12, a pendulum bob is tied to a string and swings back and forth. We're neglecting air resistance, assuming we're also neglecting friction. In that case, the only force acting on the pendulum that actually does any work, the string is 90 degrees to the motion, so it has no effect on the work, is gravity, and therefore it will be conserved. Okay, and our final one, a marble roll hits a note card and slides to a stop. Now the note card is going to apply a force. The sliding to a stop, we're going to lose kinetic energy. There's no apparent offset of increase of another form of energy. So external forces are doing work. In this case, they're causing it to slow down, so that's going to be a decrease of energy. So if you're looking for whether total mechanical energy increases or decreases or stays the same, look for external forces. If external forces are present and they're slowing it down or causing it to change its height, then most likely total mechanical energy will not be conserved. If the only force acting on the object is gravity or a spring or gravity and springs, internal type forces, then the total mechanical energy will be conserved.